Now we're going to discuss the polar bond. We've talked about ionic bonds, where electrons are given or taken between the two atom partners, as well as covalent bonds, where the electrons are shared between the two atom partners. Now, a polar bond or polar covalent bond is a little bit of both. The electrons are shared between the two atom partners, but they do spend more time going around one atom than the other. It's helpful to think about the concept of electronegativity when talking about polar bonds. Electronegativity was first conceived by Linus Pauling, who we've already talked about. And in his seminal book, The Nature of the Chemical Bond, Pauling describes electronegativity as being the power of an atom in a molecule to attract electrons to itself. Now, these aren't just any old electrons. They're actually electrons that are involved in the bond. So they must be valence electrons. There are a couple of factors that will influence a valence electron. One is the number of protons in the atom nucleus. Proton is positive, the electron is negative. So more protons, a stronger attraction between the proton and the electron. Another factor is the distance between the nucleus that contains the protons and the electron. The larger the distance between proton and electron are, the weaker the attraction between the two will be. But there's something else going on here between the proton and the electron. We know the electron's a valence electron, and more than likely there are electrons that are closer to the proton. These electrons, which are in inner shells or filled shells, will shield the outer valence electron from the influence of the proton. So we need to think about the number of protons. We also need to think about any electrons in between our valence electron and the proton. So this is very well summarized, and we can spot the trends more easily within a periodic table. Here's part of a periodic table. You can see we have the atom and below it a number. Now that number represents the strength of electronegativity. And it's particularly useful to know the electronegativity number for some key atoms that we use in organic chemistry. These would include, but not be limited to, hydrogen, lithium, magnesium, carbon, silicon, nitrogen, oxygen, sulfur, fluorine, chlorine, and bromine. Now, if we consider the periodic table as a whole, you'll notice that the smallest numbers are at the bottom towards the left. The largest numbers are towards the top and towards the right. This would make the fluorine the strongest electronegative atom. And you'll see that it has a number of 4. There is no number larger than 4.0 on the table. We need to be a little bit careful, however. You'll notice that the transition metals, kind of in the middle towards the bottom, break this trend a little bit. So it is a general trend. You're going to find some examples, specific examples that it's not true for, but generally bottom left, low number, top right, high number for electronegativity. So how do we use these electronegativity numbers? Well, if we're considering two atoms and they have the same number, well, that's going to be a covalent bond. If the two atoms have a difference of electronegativity number greater than 2, so maybe, for example, one is 3 and one is 1, then we would anticipate it being an ionic bond. So what's left? Anything between 0 and 2, well, that is going to be our covalent polar bond.